One moment. All right, we are live on YouTube, and let me just click over to LinkedIn real fast. All right, we are live on all platforms, Zoom, LinkedIn, and YouTube. I will kick it over to you, Matt.
Hello, everybody. Welcome to the Delta Lake Community Meetup. We have a great meeting today. Next slide, please. So here's the agenda for the meeting today. Michael is going to talk about the creation of Delta Lake and the history of Delta. Then I'm going to chat a bit about Delta Lake and polars. After that, Jasek's going to talk about some of the latest and greatest features of Delta Lake 3.1. Then TD is going to talk a little bit about what we accomplished in 2023 and what to expect this year. And then Nick will finish it off with Delta kernel Rust updates. If you'd like to ask questions, feel free to do that via Zoom, LinkedIn, or YouTube. We will read the questions to the presenter as they come in. And now I'm going to pass it off to Michael for a little history lesson on how Delta Lake was created, and feel free to ask your questions.
Yeah, thanks a lot. Excited to be here to talk about the creation of Delta. Like Matt said, if you have any questions, please post them in the channel because I'd love to answer some of those in addition to just talking. But I want to kind of go back in time to when we were first just starting to think about Delta. So just a little bit about me first. So I'm a distinguished engineer at Databricks. I've been there for about 10 years, and Delta is one of the projects that I led the creation of. And really the way that Delta came to be was we just over and over again saw this need from all of our customers. Basically, at the time, I was the tech lead for the streaming team, kind of building the structured streaming product inside of Apache Spark. And I was working with a bunch of the other original creators of Delta Lake, and we had just gotten to the point where structured streaming was starting to be used at large scale for doing ETL. So people really liked that Spark was great at reading from a wide variety of data sources. We could read from files, we could read from Kafka, we could read from Kinesis. You could use all of the nice data frame abstractions that people already knew and loved from doing batch processing. And now you could do them in real time on little increments of data as they arrived, instead of recomputing everything from scratch. And it turns out this was just a perfect fit for a lot of ETL problems, because I have this pretty deep belief that pretty much all ETL is streaming. People think streaming is only for like low latency, really complicated Lambda architecture things, and that's not true. Streaming is about incremental compute, and we were thinking about this a lot. The problem with doing incremental compute, though, for streaming is you end up with a lot of little files. Since you're processing data as it arrives, you're not waiting for big batches of data to arrive. Instead, you're getting little chunks and you're writing that as soon as you can go. So while Spark was great at doing this at massive scale, we were kind of just creating another problem. You would end up with an S3 directory that had hundreds of millions of Parquet files in it, and that would take an incredibly long time to query. I had a couple of cases where customers were reporting that just loading the data frame for the table would take 40 minutes, which is, looking back on that, that's just like completely crazy that you would spend that long processing metadata. And another big problem was there was really nothing you could do with all of those tiny files, because if you want, what would you do to fix this? You would take a couple of tiny files, you would read them in, and then you would write them out as a bigger file. But there's a fundamental problem with doing that in place on top of a data lake, which is what happens if you crash in the middle. You are fundamentally going to either leave extra data there, or you are going to remove data before you've replaced it with its new copy. And that was a big problem. And around this time, I was at a Spark Summit event, now Data and AI Summit. And I met my now good friend, Dominic Brzezinski, who is leading information security for a large tech company down in Cupertino. I'm sure you can learn more about it if you find him on LinkedIn. He loves to talk about Delta and how they're using it at just absolutely massive scale. But he came to me and he had in the past built this really cool detection and response infrastructure where they would collect every single TCP connection, every DHCP, every HTTP request, everything that happens on their entire corporate network, and then respond to it in real time with teams of hundreds of analysts around the globe who are experts at security and detecting incidences and threats. And he had built this in a past life, and he wanted to build it again at this new company. And so he knew what the hard problems were, but he didn't want to build it from scratch again. So he was looking at structured streaming. He kind of decided it was a great way to do this ingestion problem, but he had seen exactly this same problem that they was going to end up with tons of data and no way to manage it. And so we actually decided to collaborate. And he said, I would love to build this system on top of what you guys are building with Spark, but only if we can come up with a way to do storage. And they had a clock. They only had like 6 months before they wanted to go into production. And so, basically I came back from this summit event super excited. And we had a couple of ideas about how we were going to handle it. We knew the key ingredients were we needed to separate the kind of listing of the file system from what files are actually present in the table. Listing is not consistent. Listing takes a really long time. So we needed somewhat other way to say these are the valid files. And then the other thing we knew was that we wanted it to work at massive scale because that was, that was what people are paying us for, and that was going to be required for this first use case. So I came back and I wrote a design doc. I used my favorite trick to get the attention of the CEO, which is you email him on a Saturday morning because he's, of course, working. And he read it and he's like, I think this is really important. I think you should kind of take the streaming team and readjust them to work on this problem. So we set to it. And the first version of Delta was actually really simple. It had only a couple of kind of key ideas. One was that there would be a log that said which files were added and removed from the table. And the next idea was that you would be able to compact that log into a format that Spark could read really efficiently, in this case, Parquet. And so now, instead of having to list 100 million files, we could just really quickly read that Parquet file, feed that right back into Spark, and do our data processing. And while we were reading it, we could even do things like partition pruning, and that could happen at scale in parallel using the Spark engine. And so even with this, really simple idea that we coded up in, maybe just a couple of weeks, I think was the first prototype, we were able to take some queries that were taking hours and bring them down to minutes. But unfortunately, there was one, kind of key missing piece was this use case actually required us to do point queries that were more selective and on a column that is of higher cardinality than what you can do with partitions, right? Like partitioning is great if you want to cluster data by something very coarse-grained like date. Partitioning is not good if you want to cluster data by something like IP address, where there's millions of them. And so we had to come up with another trick, and this trick was Z-ordering. There's actually another project inside of the company that had shown that if you order data within the files in this really kind of clever way, where rather than ordering it by only one property of the data, you kind of interleave all of the properties you care about and order by that. This is the idea behind Z-ordering. They had shown that you could do these point queries very, very quickly. And so we kind of, again, we were like pressed up against the clock. So we set to take this code base and just re-implement it on top of Delta's metadata. And that was the magic trick. That was the thing that got us from queries taking 15 minutes down to 1 minute, which was the target we were aiming for. And we closed this first big deal in Databricks' history. A couple of other fun facts. When we first created it, we had to come up with a name for it. So we called it Project Tahoe internally. This is another trick. If you want people to think what you are working on is important, you give it a clever name so they remember it. And we picked Tahoe because our goal was massive scale. And for those of you who aren't familiar with California geography, Lake Tahoe is a lake up in the mountains near the Bay Area. If you like to ski and you live in San Francisco, you could definitely know about it. And it's kind of interesting because it is an absolutely massive lake. it's not that big, like in circumference, but it is incredibly deep for its size. And there's actually so much water in it that if you were to spread it out over the entire state of California, we would be standing in over a foot of water. And I had read that fact recently, and I thought it was kind of cool and conveyed the scale that we were trying to get to. And so we initially called it Project Tahoe. And if you look in the code base, I think Tahoe, the name remains all over the place, just because once you write code, it's almost impossible to get rid of. And so that's the story. I'd love to take any questions or yeah.
Thank you very much, Michael. Yeah, we'll let some questions trickle in as the other presentations go on, and then we'll get them to you afterwards. That's great. Thank you for the Delta Lake history lesson. That was fascinating. Next slide, please. Okay, cool. So now I'm going to chat about Delta Lake and polars for just a little bit here, which is a cool way of using Delta Lake that does not require a Spark. So let's check it out. Next slide, please. So why is Delta Lake great for polars? Well, all the features that make Delta Lake great for Spark also carry over to polars as well. So we have version data, time travel, rollbacks. Those are great for polars users. Now, one thing that's also great about Delta Lake for the polars community is that it's great for maintaining data quality, such as schema enforcement and constraints. And similar to what Michael was talking about, the file listing problem with data lakes and how Delta makes that better. Polars users also get that benefit, and we'll talk about file skipping and faster file listing that Delta Lake provides polars users. Next slide, please. So let's just see this in action with a quick little example. So here what we're doing is we are instantiating a polars data frame. It has a single column of data called X with 3 rows of data, 1, 2, and 3. So we're writing that out to a Delta table with that built-in write Delta method that's right in polars itself. And then we're just reading in our Delta table into a polars data frame, printing it out to verify that it's been successfully created. Next slide, please. Now we can see how we can easily append some data to this Delta table with polars. So we're going to instantiate a separate polars data frame with a single column X and 3 rows of data, 8, 9, and 10. And we're going to use that same write Delta method that's built into polars. But this time we're going to set the save mode to append. So what that's going to do is to append the data to the existing Delta table that we initially created with polars. So now we can read in that data and see that our Delta table now contains 6 rows of data, 1, 2, 3, 8, 9, and 10. Next slide, please. So now let's overwrite the Delta table. So we are going to instantiate a third polars data frame, same schema, so a single column X and 3 rows of data, 55, 66, and 77. And then we're going to write that out to the Delta table, and this time the save mode is going to be set to overwrite. So what that's going to do is it's going to logically delete all of the existing data and append some new data. Now, a logical delete is different than a physical delete. So if you do an overwrite transaction with a data lake, you actually need to physically remove the files. So when you're dealing with a Delta table, you can just say, mark those files as removed and not actually physically delete the data. So now when we read in this data, we can see that we have a single column X with 55, 66, and 77 as expected. Next slide, please. So now let's check out time travel. As I was just kind of alluding to, we didn't actually physically delete the data from the earlier versions. So now we can still read it in. So there's 3 versions of our Delta table. Version 0 was the one we originally created. Version 1 was when we made the append of the data 9, 8, and 10. And then the third version was after the overwrite transaction. When we go back to version 1, we can see that it still has those 6 rows of data. And then we can see that when we're reading in the Delta table at version 0, it just had that first 3 rows of data from that initial creation. Next slide, please. Now let's check out Delta Lake schema enforcement and how this is kind of helping us maintain the integrity of our data. So let's instantiate another polars data frame. In this case, it has a column Y with 2 rows of data, A and B. And we're going to try to append this polars data frame to our Delta table. And we can see that this is going to result in an error. The error is value error, schema of data does not match table schema. So we can see that what Delta Lake is doing is saying, hey, you have this data table. It has a single column X. You're trying to append a data frame that has a different schema, and I'm rejecting this transaction because the schema is off. Now, data lakes don't have this sort of protection, so they're kind of easily corruptible. So this is quite nice for maintaining the integrity of your data. Next slide, please. Now let's check out another Delta table that has two columns, name and age. The name column is a string and the age is an int64. And what we're going to do here is we're going to add a constraint to our table. So we're instantiating a Delta table object, and then we're using the alter.addConstraint syntax. That's going to take a dictionary of constraints. The keys are the name of the constraints, and the value are the predicates, which specify what the constraint is doing. So in this case, we're saying, hey, in this table, we don't want any values in the age column that are negative. We only want to allow positive values in the age column. Next slide, please. So let's see this constraint in action, see how it's working. We instantiate a Polars data frame with those two columns, name and age. And we can see that one of those rows has a negative age. So now let's try to write that data frame to the Delta table using Polars. And we need to set some Delta write options to make sure this works properly. And we can see that that's going to cause an invariant violation. Check or invariant age is greater than 0 violated by row. So we can see our constraint is working as expected. We're not allowed to append values to this Delta table that contain negative values. Next slide, please. Okay, cool. So now we're going to take a quick look at how Polars queries can run faster with Delta Lake. This is just a little benchmarking analysis I ran on my local machine using the H2O dataset. So this is a dataset with 1 billion rows. When it's stored locally in an uncompressed CSV file, it's about 50 gigs of data. So I took that CSV, I converted it to a Parquet file, and I ran a filter query followed by a group by aggregation on the Parquet file. And we can see that that executed in 8.3 seconds. Now that's pretty fast. Polars obviously is an intelligent query engine and is taking advantage of Parquet row group skipping. But now when we take that same data and store it in a Delta table and run the same exact query, we can see it runs in only 3.5 seconds, which is quite faster. Now, the reason the Delta query is running faster is because Delta stores data in separate Parquet files, and Delta can look at the transaction log and intelligently skip entire files prior to doing the row group skipping. So very often you'll get Delta queries that run a lot faster. And as kind of Michael was alluding to earlier, you can z-order the data to make this even better. Next slide, please. So the community is doing some really cool stuff with Polars and Delta Lake now. This is a blog post from the other day about somebody who's doing type 2 SCD upserts with Delta Lake and Polars. So as you can see, the community is really running with this integration. Polars is a pretty popular query engine, and folks are loving this integration. Next slide. So now I'm going to pass it off to Jacek, who's going to talk about some cool new Delta Lake 3.1 features.
Thank you, Matt. It was nice to hear about non-Spark Delta implementation, and that showed me when all this non-Spark implementation appeared as part of official Delta Lake repo. It reminded me that Delta Lake is all about this little protocol that describes how to save files onto something that's in the cloud. And Michael earlier described the reasons why there are some design approaches to this problem of even listing files in S3. There are some limitations like 10K files at one hit to this S3 bucket service, and so on and so on. So we've got this Delta Lake, and I'm Jacek Laskowski, and after years with Spark SQL and Spark Success Streaming, I decided to invest my time into into what led to create Delta Lake. And it was also the time when Databricks, I'm not part of Databricks, but it's a Databricks heavy show, but okay, so a little bit different flavor. So the Databricks at some point closed some features that were not available up to just a week ago. And I'm speaking about some features that caught my attention, but I couldn't really understand what these features meant or should mean for people using Databricks / closed Delta Lake implementation. So I couldn't wait till Databricks and the team behind Delta Lake open sources, liquid clustering, for example, or some other cool table features. And so this slide is all about all these discoveries that I finally, and you guys too, listeners, can have a look at and really understand the value propositions behind all this, buzzword-like announcements like liquid clustering is going to change your life, how you manage your data, blah, blah, blah. Okay, I don't buy it unless I see the code. And I could finally see the code. This code drop was, a week ago. Well, it was earlier, but finally I realized there's this release candidate 1, 2, 3, and after this we've got 3.1. And finally, so Delta Lake 3.1 comes with lots of internal changes. Might not necessarily be visible to end users who just use Delta Lake to version the data, optimize it with different commands. So this user frontend might not have changed that much, but from internal code perspective, there are lots of great changes, like, for example, table features table features. It's a brand new concept. Might not necessarily be brand new in 3.1. It may have come out as part of 3.0, but it's fairly new compared to other features that were available in Delta Lake. So table features and all these links, I am not going to say next slide, please, even though I did, but please do not, Carly, change the slide. So what I'm trying to say is that all these pointers are all these links point to descriptions, deeper descriptions of what I could find in the source code of Delta Lake 3.1 in particular. So I cannot show it because I'm not in control, and I don't want to mess this presentation too much. But just know that under all these links there are descriptions of. How can you go back, please?
Sorry, I thought you said it too advanced. Going back.
Yeah, I did. And that is a coincidence because we should look back or go back, I should say. Okay, thank you. Yeah, thank you. So Delta Lake 3.1 came out a week ago. There was this official release with lots of table features. Some are marked as in development, like row ID, something that caught my attention too. But out of these table features, which are basically extensions to protocol, or shall I say, protocol upgrades, for people who are not familiar with what protocol means in Delta Lake world, it's just to say who is able to read or write to from a Delta table. So you can just control or limit features by installing them and then dropping out some clients who are not able to read a particular feature because, well, it's not supported by client code. That also showed me this table feature showed me how fragile, shall I say, or quite the opposite is this protocol. It just says what it's going to do in version 7 or version 8 and how much impacts it readers and writers. So this is all about table features. And they are usually turned on and off, enabled and disabled via certain user visible, sometimes marked as internal switches or table properties slash Spark session configuration options. So you can control it from a user perspective without having a deeper look at the code. And one of the table features that caught my attention very early, once it appeared in the repo, was auto compaction. If I'm not mistaken, auto compaction was part of Delta Lake 3.0. I might be mistaking all these versions. Things have been changing quite a lot and at quite a fast pace lately, for good. And so auto compaction puts heavy use of something that was available in earlier versions of Delta Lake, but it's not available for end users. And I know that some devs, some committers of Delta Lake, they are not ready to open it to users to install some extra post commit hooks. So for now, just know that there is an infrastructure in Delta Lake that allows you to register that something should happen after transaction is committed, after the transaction is done. Okay, and by done I mean successfully committed. All the changes are successfully committed, and basically table is ready. Table is in another version. So you could, in theory, register another post commit hook, but it's not yet available for us mortals and users yet. I'm pretty sure that at some point it's going to be open source, in a sense that it is part of open source Delta Lake, but it's not available for end users. But one of the cool uses of post commit hooks is this auto compaction. What it does, it's basically what the name says. It can do extra optimization at right time, which, if my understanding is correct, I didn't confirm it with the devs, with the crew behind Delta Lake, makes writes heavier. So if you enable auto compaction, for example, by turning it on, it means that your writes are going to be heavier, meaning it's going to take longer times, right? So just know about impact of auto compaction or other table features being enabled. So auto compaction caught my attention. It's good because you don't have to run all these extra commands like optimize to compact smaller files. Another optimize or shall I say optimize based table feature and also using post commit hook is liquid clustering. When I first heard about this nicey, catchy term or phrase, it was like, come on, Databricks is doing it again. It's just giving something to end users without telling us exactly what it's doing under the covers. And what I mean by that is that I couldn't have a look at the implementation of this liquid clustering. I knew they figured some clever way, but they were teasing me with something clever in Delta Lake being available, but it was still closed. Finally, in Delta 3.1, liquid clustering, aka cluster tables, this feature is fully available in a sense that it's still marked as not production ready. It's written in the code. So yeah, please correct me, the Delta Q, if it's still applicable or not, but this is still in the code of Delta Lake 3.1. Yet you can get a feeling of what's coming once they decide, perhaps in Delta Lake 3.2 or 4.0, to mark it as production ready. So what is liquid clustering? Basically, Michael mentioned z-ordering as one of the optimizations they added in Delta Lake. But another optimization, something that I'm still learning and deepening my knowledge, is another, how they say, Hilbert curve based optimization. Okay, so they basically decided to extend what's possible with the what's possible in Delta Lake to optimize our point queries, and added this liquid clustering, which basically is another curve to lay out our data by, and Hilbert curve. The other one was Z order, and basically made this available again at post commit as part of this post commit hook set. And so once you enable liquid clustering, you can get something that's very similar in Delta Life tables. Another cool feature I'm yet to discover by source code once Databricks decides to open source the code behind Delta Life tables. But just know that they are doing some crazy stuff at write commit or at certain moment in time. And now liquid clustering is basically the very same thing. In other words, they apply some optimizations at commit time, at write time, to make our queries, future queries, faster. In other words, you just basically, with liquid clustering, execute optimize command, and this optimize command with certain certain features will get executed without human intervention at commit time, which is pretty cool. Wish I had full control of these links and slides, so I could just poke around and show you all these nitty-gritties behind this simple slide. But just know that there's so much to be discovered yet still. And finally, we got what Databricks promised for long. In Delta Lake 3.1, we've got liquid clustering and some other earlier closed features. So it's a good thing. And the last, okay. The last thing I want to point out is that Danny Lee posted yesterday on LinkedIn a nice, fine article about how Delta Lake liquid clustering conceptually works. So if you want to get deeper understanding of liquid clustering, you can have a look at the source code or just read some fine articles like the one from Danny Lee. Thank you.
Thank you very much, Jacek. That was wonderful. We got to get you for a deep dive soon. All right, let's pass it over to TD. Next slide, please.
All right. Is that my turn now?
You're up.
Oh boy. Okay. So Jacek, thank you very much. It is always a pleasure to hear a deep dive from you. I'm going to touch a bit of the same topics, but cover things that is broader, looking back at the entire 2023. And actually, I have some interesting thoughts on some of the things you said, and maybe that's a conversation we should start anyways about liquid clustering and post-commit hook and stuff. Absolutely appreciate your thoughts. But okay, looking back for the entire year, it has been an amazing year. So we are right now at 18 million downloads per month, and this is downloads spanning Maven, PyPy, for Spark, for Delta Rust, the Delta Lake PyPy shim of Delta Rust, spanning everything. And this is a 1.6x growth in adoption, which is amazing. Like even companies are not growing as fast in this economy as Delta is growing, which is amazing. So now you can see that there has been a huge frequent releases spanning the entire year, both on Delta Spark. There's also Delta Trino, which I kind of did not cover this because it will make the slide too cluttered. There is Delta Rust, who's at its Python thing. All of it, there's a lot of innovation happening. So to discuss and give an overview of this, I've kind of broken down the innovation work that is happening into 3 themes. Next slide, please. So there is feature innovation. I'm going to talk about it. Jacek covered a little bit, but I'm going to expand on it further. There is performance and there is interoperability. Next slide, please. Regarding feature innovation, yes, you have all heard about liquid clustering by now. I think the additional context here is that we are in halfway point of adding liquid clustering. The missing piece right now from 3.1, which will eventually make it to 3.2, is not just the Hilbert curve, but this new concept called Z cubes. The major challenge of optimize Z order was that every time you run optimize Z order, it used to reprocess things that had already been Z ordered. So the write amplification was very high. So rather to reduce the write amplification so that you don't touch things that have already been nicely clustered, we're introducing this concept called Z cube, which makes these Z cubes of 100 GB of data, plus minus, such that once that 100 GB is nicely clustered based on the columns you specify, it will not touch that data once again. It will only find out what are the new unclustered data that does not fill a nice 100 GB Z cube and only cluster those the next time you run optimize on it. So that's the other piece that is being built right now. And so, Jacek, you'll soon see the code. So column, other things like column defaults, like now you can specify that for a column, you don't have to specify the value at the time of insert. You can, it knows what default values it can be assigned to. You can define expressions on it and stuff so that it is automatically assigned if it's not specified. Table cloning is another very nifty feature where you can make a shallow copy of a table. Basically, just we copy the delta log into a new delta log that points to the same underlying Parquet files. And now this is an independent copy of the entire table, and any changes you make to this will basically is copy on write effectively. Like any new Parquet files will be for the new table, but it'll keep pointing to the old files as needed. So very useful for quick experimentation. You don't have to touch the main table, but you want to make a quick copy of it and start playing around with the table, modifying it, etc. to experiment. Great, very useful feature. We made a huge set of merge improvements, both in terms of API. We added a new clause called when not matched by source. Now, this is the most advanced merge, distributed merge implementation to the best of our knowledge across any formats. We also added idempotency in merge because it's common in a lot of use cases where you're upserting batches of data from, let's say, structured streaming, and you want those merges to be idempotent. Things that have been updated, you don't want to double update them or stuff. So that is added. We added support for SQL operation table changes to get the row level changes between two versions. So there's a lot of things that are user facing. Underneath the covers, next slide, please.
5-minute warning, TD, just as an FYI.
Wow. Okay. Then I'm going to speed up. So yes, Jessica talked about table features that powers a lot of new protocol changes that are coming in. There's checkpoint v2 log compaction that are taking the reliability and scalability of the log to not just tens of millions files, but 100 million plus 1 billion files. Then there is deletion vector, which is our version of merge and read solution, and we think it's the best merge and read solution possible. Next slide, please. And I'll come to the deletion vector performance soon, but there has been also innovation going on outside Spark. There is Delta Flink, where we added Flink sync, source SQL support, which is being used in DoorDash at a very massive scale, 220 terabytes per day in real time. Trino has been making huge strides in innovating on the performance and the protocol support, deletion vectors, column mapping and stuff. Next slide, please. And of course, Delta Rust, all the things that you have already heard Matt talk about, Polaris and stuff is based on the Delta Rust. So it has been adding a lot of operations that was till now available only in Spark, which is amazing. You don't need Spark to do these operations. We also have a new connector, Delta Go, contributed by Rivian. And so, the ecosystem expanding beyond the JVM very, very, very rapidly. Next slide, please. And then coming to performance, deletion vector is basically these delete, update, merge operation on steroids. Why it is the best that we think? Because you can get almost an order of magnitude improvement in merge, update, delete performance without any loss of read performance. So conventional wisdom says that, oh, merge and read is write optimized, read will be slower, and copy on write is read optimized, writes will be slower. That is not true. With this approach of doing merge and read, you can get the best write performance possible without sacrificing read performance. Next slide, please. And then Jessica talked about auto compaction. There's optimized write. These two pieces of the same puzzle where we want to make sure that even if you don't run your optimized compaction job offline on a daily, weekly basis, you don't want the quality of your table, quality of the read performance, small file problems to deteriorate over time. And optimizes every write job to create larger files. And auto compaction takes care of any previous smaller files that were left over. It just mini compactions every time you write into the table. So together they can get much better out of the box read performance all the time. Next slide, please. And then the third theme has been interoperability. Interoperability in one way between formats. So we released this idea of Delta Uniform, where the core idea is very simple. All these formats, Hoodie, Iceberg, Delta Lake, they're all just Parquet files underneath, and they only differ pretty much, like there's some details I will not go into, but they differ in basically how they manage the metadata in the form of their own logs and stuff. So why not just make it easier for people to read the same underlying table data in different formats by creating the metadata from different formats. So with Delta Uniform, it's a very fast setup to enable Delta Uniform on a Delta table, and you will be able to read Delta table as Iceberg tables from any system which can only read Iceberg tables. It is quick, it is automated, it's really out of the box, very simple. And then we can also convert Iceberg tables to Delta if you want to try out Delta very quickly, and it can be an in-place conversion without rewriting any of the files. And then next slide, please. In terms of extending the interoperability across engines and connectors, one of the problem we faced is that as we are evolving these protocol changes like table features, deletion vectors, etc., then it is very hard for any of the protocol implementations to keep up with all these changes coming in. So it is, and what that leads to is a little bit of fragmentation in the ecosystem. Some connectors are left behind because they're not keeping up as quickly. Some connectors don't support certain features, bugs get introduced in different feature implementations. Now, to solve this problem, we started a brand new project called Delta Kernel. Next slide, please. Which, what it's doing is actually, previous slide.
Sorry, going back one moment. Keep going, TD. I'm headed back.
So what the idea of Delta Kernel is that instead of you as a connector developer building the connector using the protocol implementation, implementing it directly, rather we provide you a library that abstracts out all the Delta protocol details so that the connectors don't have to care about it. So all you need to do is build a connector once using this library. And after that, you can just keep upgrading the library version and you will keep getting the latest features, latest protocol features in the Delta format without having to really understand or care about what changes are happening underneath. So DVs, how it works, you don't need to understand. You just upgrade the kernel to using kernel, you get the best performance already. So next slide, please. I won't go into a lot of details in how the kernel works. There's a separate talk for that. There's a link to this slides. Hopefully the slides will be published. But basically, the idea is that it's a very narrow API. The connectors say, here is my query columns that I want to read, here is my query filters, and kernel gives back table data in batches, columnar batches, and the connector doesn't need to know whether it's reading from one file, multiple files, are there other files, Parquet, or in future, who knows what type of file type. It doesn't need to care about that. Next slide, please. So this has been a major focus over the last year and will continue to be the focus. So we're building kernel in two flavors, Java for the JVM ecosystem, and we have had a couple of releases. And then there is Rust, which is prototyping in progress. And the next speaker, Nick, is going to talk a little bit more about what are the unique challenges that building such a library in Rust presents itself. Okay, next slide, please. Okay, now.
TD, so Nick has to go and then we got a bunch of questions. So
okay,
just flagging that.
I'll finish in 2 minutes. I just have 2 more slides.
Okay, cool.
So in 2024, I think what I want to leave the audience with is there are 2 major discussions that are going on right now. Next slide, please. In the next year, one of the major changes in the ecosystem coming is Spark 4.0. And Spark 4.0 makes a major change in the Spark Connect. So, and it always breaking changes. So we're considering whether to release a Delta 4.0 on Spark 4.0 in order to accommodate those breaking changes, which may have to require our changes, require our APIs to break as well. And next slide. In terms of features, there are few themes that are currently in discussion. One is more flexibility in how data types are handled, like allowing the data type to evolve as there is more and more semi-structured data. And then in terms of commit management, there are how is a table managed in terms of who can commit and who is the owner of the table is also something that is under discussion. It's you can comment on the issue linked here. And the next slide, please. And the third thing is the kernel connector ecosystem. We want to work with every connector developer out there to help them to adopt this kernel Java and kernel Rust. And Apache Druid has already adopted it as of a couple of weeks ago. So yay. So this is going to be a major themes of the next year. All right.
Thank you very much, TD. Nick, you got 4 minutes. Sorry.
4 minutes. All right, I'll see what I can do. Next slide then. So I'm going to go really fast. Oh, these slides are not the ones that I've updated. Can you reload the slides? There we go. Thank you. So what I want to talk about, and I will have to skip some of this, but I'll give a brief bit of background on what we're trying to do. Talk about what we've been working on. I will probably not do the technical examples if I take too long, and then I'll talk a little bit about the roadmap. Next slide. So a little bit about why we're building a kernel in Rust. So the main goal is that we want to be able to support native languages, not just the JVM. So connectors written in C, C++, Python. You heard about polars, things like DuckDB, and others. And there's kind of a unique challenge here that I wanted to talk about. I won't probably have much time to talk about it, but is one of the things that we're working on is how we pass data between the connector and Rust in a safe way. Rust makes you think really hard about this. It's one of the reasons that we chose Rust. You have to really consider your memory management carefully. This is great because we don't want connectors to crash. We don't want use after free bugs in connectors. These are things that need to be really solid. So I'll talk a little bit about that. Next slide. One of the things we've been working on is expression handling. I want to thank Robert Pack, who's one of our open source contributors here. He's been doing a lot of work on this. There's a couple main goals here. One of them is removing deep reliance on Arrow. Arrow is great. We definitely plan to continue to use Arrow in our sort of default implementation of the kernel, but we want to not enforce any particular format. So we were kind of abstracting Arrow out. And we'll obviously continue to use it in our default client, but we don't want to keep the dependency forever. Next slide. We've also been working on building out the foreign function interface, like how we're going to call into and out of the kernel in C. We did a hackathon last year working on integrating DuckDB, and that brought forward a number of the issues that we've been working on. Ryan Johnson's been doing a lot of work here, thanks to him. He's been working on how we do iterators, how we pass schema, and how we do expression passing as well. Next slide, please. So I guess I have 1 minute, so I'll try to go really fast here. But sort of one of the big and interesting technical pieces, I think, that has come out of this prototyping is rather than allocating some data and trying to hand it across to the engine or connector, or allocating on the engine connector side and handing it back to the kernel. The idea is that you have your internal representation and you manage that memory, and then you allow the other side to basically ask to visit it, and it will get callbacks. So I'll go really quickly through an example. Next slide. So this is like, hey, I have a schema on the kernel side. So the kernel is, say, parsed the table schema, and it wants to communicate it back to the engine or the connector. How does it do that? So next slide, please. So the basic idea is that the engine is at the point in its query execution where it needs to know, hey, what's the schema for this table? So it'll create a visitor. This visitor has a few callback methods that we specify in our API. And it says, hey, kernel, can you please like visit the table schema with this visitor. The kernel says, sure, I know like the methods that you have on your visitor. I have a schema, I'll traverse it. Next slide. So that will then, as it's traversing the schema, make callbacks to the engine. So it'll start traversing its schema and say, hey, I have a string, I have an integer here with whatever extra metadata that you need. Structs are a little bit more complicated. Once we finish, like fully open source, you can go look at how we do it, but it is possible. And basically, the key thing here is that, next slide. When we return from visit schema, the engine doesn't have to assume anything about the memory management of the schema on the kernel side, right? Because internally, it's been building the schema with its own memory space. And then it can finalize that engine schema and just use it. And so now there's a really nice separation where only for sort of the length of this flow chart does the data have to stay alive on the kernel side. It may live longer, it may not. It's just there's no enforcement of who manages the memory. There's no worrying that like the kernel allocated something and the engine didn't free it, anything like that. So it gives us a really clean way to allow passing this data back and forth without causing problems like use after free. Next slide. I think I'm already over time, but I probably will skip this one. I'll just mention very briefly that previously we were trying to do sort of data passing by requiring engines to provide a fairly thick sort of column or batch API that let the kernel really poke at the data in very detailed ways. We're trying to switch to more of a thin, opaque data model, so you can have anything you want on the engine side and use a similar kind of visitor API to let the kernel pull out the bits of data that it needs. Basically, hey, engine, can you please visit these pieces of data for me? And only passing primitive types back and forth between the kernel. There is an example on the next slide if you can go to it. I won't walk through this one, but feel free to look at it and hopefully it makes sense. So next slide, I will be really fast. This is my last slide. Just talk very briefly about the roadmap. We're very close to open sourcing so that people can look at it. We want to get this data passing stuff finished, the FFI stuff finished. Those are sort of in progress and almost there. We're looking at getting full basic read support based around that, followed with Python support, data skipping, all the kinds of things, and building out connection engines. So this is not in exact order, but these are the basic things that we want to be working on over the next months. So that was extremely fast. Sorry for the lack of details, but I'll leave it there. Thank you.
Thank you very much for the accelerated version. Cool. Let's dive into the questions. First one is for Michael. How does Tahoe relate to the Delta protocol?
It's the same thing. We just called it Tahoe originally, and then just decided that wasn't a great like project name for it overall, and it became the Delta protocol. But like it literally just extensions to the Tahoe protocol became Delta. The basics of add file and remove file and metadata and checkpoints have all remained the same.
And maybe for some curious listeners, what is the Delta protocol at a high level?
The Delta protocol is it's the protocol that we use to write the transaction log in a Delta table. So it describes each version of the table in order, and it describes how the table has changed since the previous commit. So it is things like add this file to the table, remove this file from the table, change the schema of the table to this, and now much more exotic things like add this deletion vector on top of this file that already exists. But it is the way that different, like, so Nick was just talking about the Rust Delta implementation that speaks to the Scala Spark implementation of Delta through this protocol, which is the transaction log that is written to the disk.
The Tahoe is kind of like V0 of the Delta protocol, and the Delta protocol is like evolving over time as new features are added. Got it. Wonderful. So next one, maybe this is a good one for you, TD. Anything on Delta standalone for Java Scala and filtering and fetching data on partition keys?
Okay, very, very specific question, but okay. Very good question. Okay, so Delta standalone was our first attempt to build such a library that other connectors can use to build that connectors can use. But we learned from the insufficient design choices we made with Delta standalone, and that led to Delta kernel. So Delta kernel is like a philosophical V2 of Delta standalone, and we encourage everyone in the community who are using Delta standalone for a connector to migrate towards Delta kernel, because Delta kernel is going to be the future. Delta standalone is insufficient in isolating the connector from all the low-level Delta protocol changes, whereas Delta kernel is designed for that. So to future-proof your connector, migrate to Delta kernel.
Thank you very much. All right, this one's for you, Nick. What is the difference to Spark? Presumably that's in referring to polars. So what is the difference between polars and Spark?
The difference between polars and Spark? I don't think that should be a question for me. Matt, you're better at answering that.
I'll take it. So I think they're both query engines. I think Spark is a query engine that's meant to be run on a cluster. It can be run on a single node or also a cluster. I think Polars is more a single node query engine. And both can interact with Delta tables. Cool. So I will leave this last question up for whoever wants to take it. Did he just say liquid clustering is now open sourced, or did I mishear?
It is open sourced, but the implementation is in progress. There are pieces that we are still implementing and testing in open source on Apache Spark. You can kick the tires with 3.1, but the full version is going to appear in 3.2.
So Michael, how does, so we were just talking about Tahoe and the Delta protocol, and now we're talking about liquid clustering. Like, how does liquid clustering relate to the Delta protocol?
These are all just extensions of the Delta protocol. Although, what did we change? Actually, I don't know specifically. What did we change in the Delta protocol for liquid? Or is it just a better use of the Delta protocol?
I can explain that. So for what we did in the Delta protocol is made the protocol aware that there is a concept of clustering, that this table should be clustered by these columns. And this is the technique of clustering that should be used. So we made the whole clustering as a concept pluggable in the log. So the log specifies that here is how this table is clustered. So if you want to write to this table or cluster data on this table, use this particular style of clustering. And liquid with Hilbert and Z-cube is one such style of clustering, but the protocol allows you to plug in your special form of clustering as well if it works better for your data.
Yeah, it makes a lot of sense. So then I guess maybe I'll repeat and see if I understood. So the change to the protocol is that now clustering is actually a property of the table rather than something to just run one off with the optimize command.
Yes.
But the actual clustering that is happening is all happening within the original protocol because we're just adding and removing files that now have a better clustering to them. And that's that's something that was always possible, even in Delta or Tahoe 0.1 or whatever.
Yeah.
Cool.
Sounds like Tahoe 0.1 was well specified. Wonderful. We're getting back to the presentation. We got to close it out, everybody. So I'll answer the rest of the questions offline. Hey, thanks everybody for joining. Really appreciate your attendance. Make sure to check out the Delta Lake Definitive Guidebook that you can check out with a free trial on O'Reilly. And is there any other slides? Next slide. Oh yeah, next steps. If you'd like to join our community, feel free to join our Slack. I think we have about 10,000 people there. Join our LinkedIn. We got like 40,000 followers. We post all the time. Follow us on X. That's apparently still a thing. The Delta Rust folks like the Mastodon stuff. And we have a public roadmap that is maintained by the Linux Foundation, which you can check at that link. So really appreciate everybody's time. Thank you all for coming and hope everybody has a wonderful day. Bye-bye.